Okay, now we're going to talk about the disk method. That is, finding the volume of a solid of rotation by slicing it up into disks. We'll use the most general example possible. Well, one of them. Suppose we take the area between the x-axis, the curve y equals f of x, the line x equals a, and the line x equals b, pink like that. We're talking about the area inside there, and we rotate it around the x-axis. So here's another copy of it. If we rotate this area around the x-axis, it's going to come down around to form that shape when it's all the way down, and then it's going to go back up and around, and it's going to sort of form some sort of weird shape like this. If you tilt your head to the left, you could almost imagine it was sort of a pedestal. If you tilt your head to the right, it almost looks like a crazy heel on some sort of fancy pump or something. I don't know. In any case, how do we find the volume of this weird object? It's not anything that we've seen before. It's not a prism. It doesn't go straight up and down. It has different lengths. Well, here's the trick. Just as we calculated this, we estimated this area by slicing it up into slices, we can slice this volume up into slices. Let's take an example. Let's do it in red. Let's just take one of these slices here. One of these slices here is going to correspond with 1, 2, 3, 4, 5. I'm not doing this perfectly, but have some kindness for me. It corresponds to, let's say, this slice here. And as this slice rotates around, it's going to come down around like this, and it's going to form a shape that is, well, let's pull it out. Let's pull it out and redraw it. It's going to pull out, let's do it in black though. It's going to be a shape that's an awful lot like a cylinder. Almost. It flanges out a little bit, but it is approximately a cylinder. Just as we added up this area by pretending that each one is a rectangle, well, we could do the same thing actually. We could use the right endpoint and treat this like a rectangle. And, ooh, I'll have to do this in green. We could use the right endpoint here and get a slightly larger cylinder. Something that kind of adds in this little bit here. So we end up with a cylinder. And what are the dimensions of that cylinder? Well, over here, if we chop the distance from A to B up into n different pieces, it's B minus A over n wide. And so this one is also going to be B minus A over n wide. And, well, that's sort of the height of the cylinder, right? We've got the cylinder like this, more or less, and it's B minus A over n thick. And we need to know its radius. And here's the cool thing. The cool thing is that the radius from here to here is the height. It's exactly this same, how do I do this in green? It's this height. And that is just what you get when you plug into your function. What do you plug? Well, however many slices this is, you've added that many B minus A over n's into the function. So that is, why don't we call it this way? The radius is f of x star, let's say x star, where the x star is this coordinate. That's superscript, subscript, x star is that coordinate. So, in general, in this particular case, what we have is, it's what you get when you plug, what is it? We plug into f, it's what a plus I, b minus a over n. Okay, and so what is the volume of this? The volume of a cylinder is, as we said before, what is it? Pi r squared h. So it's pi times f of a plus I, b minus a over n you plug it into the function, and then you square it, and then you multiply by h, which is b minus a over n. A looks demented. B minus a over n. Now that is just the ith slice. This is, this is the first slice. This is the second slice. What we're talking about here is the ith slice. And what we want to do is we want to add them all up so that the volume is approximately what you get when you add up all these slices. It's approximately the sum I equals 1 up to n of all these volumes. Pi f of a plus I b minus a over n 1, 2, 3 squared times b minus a over n. It's approximately what you get when you add up all of those. Hey, but if you don't want to be approximate, if you want to say equals, you just do this, the limit as n goes to infinity. And if you're thinking what I'm thinking, and I bet you are, you're thinking, why don't I take this b minus a over n that doesn't have any i's in it, and therefore it's the same when I is 1 and 2 and 3 and 4 and 5. Why don't we pull that out front, and then we get b minus a over n, and then the sum I equals 1 up to n of just, now I'm going to keep the pi in there just for my own nefarious purposes. Pi f of a plus I b minus a over n to square that whole thing. Because I know what you're thinking. You're thinking, this is a Riemann sum. This looks totally like a Riemann sum. This is a Riemann sum from where the function is not f of x, it's pi times f of x, the whole thing squared. And that is, in fact, therefore, see, before we've always gone from integrals to Riemann sums. Now we go the other way. This is the integral from a to b of pi times f of x squared dx. And if you're like me, you don't want to have to deal with Riemann sums. We can take integrals. And this is lovely. So, in a nutshell, the question is, if we take the area around the x-axis and rotate this curve around, what is the answer? The answer is the integral from a to b. We can put the pi out front. We take the function, we square it, dx. And just think of, we take our function, y equals f of x, from a to b. This isn't as correct, but if you rotate it in your mind, and you look at the thinnest possible at one particular point, x star, I know, it's just a line, it will form a circle, a two-dimensional circle. And the area of that circle, I've had enough red, the area is going to be pi times whatever you get when you plug that value into x, into f, pi f of x star squared. And if you think about that, and if you think, I want to add these all up from x equals a to x equals b. It's almost like making a stack of paper, of sheets of paper of different sizes, and stacking that one, and this one, and this one, and this one, and adding them all up to get your solid of rotation. Then you think, we add them all up with an integral from a to b of pi f of x squared dx. And I'll do some examples.